Today I want to work with you on lesson 5-7 out of the book, and I want to start by saying that I don't think the book does the best job in explaining this. And so Mr. Harris and I have gotten together over the years and we have talked about what would it look like or be important for you to know to be successful in solving these trigonometric equations. And so I do this a little bit differently than the book. And so if you want to read about this lesson in the book, that's fine, but they're going to show you some different techniques for solving than I'm going to show you. We're going to work almost exclusively with the graphing calculator to try to solve some of these problems today. But before we start, I wanted to start back with a problem that you had in your homework for today, which was on Lesson Master 5-6, and it's this problem that we have right up here on the overhead. It was 1/2 times the tangent of 5 theta is equal to 3. Now I had given you a window and I had told you that I wanted you to look at this for theta that lies between -90 degrees and 90 degrees. So I gave you a suggested window, and then you might recall that you got 5 solutions to this problem. Well, I wanted to start by saying that we have to have a way to solve equations so that we know exactly how many solutions we're supposed to have, and so that we have a way to write them in what's called the general form. And the problem with this particular question that you had on your lesson master was that it's not that you couldn't solve it by hand, but that when you did solve it by hand, you would only get one solution. And so to solve this by hand, we could multiply both sides by 2. We'd get the tangent of 5 theta is equal to 6. And then, of course, to get rid of the word tangent, we would take the inverse tangent of both sides. So if I take the inverse tangent of this side, I have to do the same thing to this side. So 5 theta is the angle whose tangent is 6. And then, of course, I'm going to divide by 5. And so my theta is going to be the angle whose tangent is 6 divided by 5. Well, if I jump over here and employ my calculator to help me with this, and I tell my calculator, now I'm going to make sure my mode is in degrees. Okay, so that's good. I'm going to tell my calculator I want to take the inverse tangent, or the angle whose tangent is 6, and divide that by 5. Then I get for an answer, and you might remember that you got for an answer as well, because you're supposed to round it to the nearest hundredth, you got 16.11 degrees. So that would be my first answer, 16.11 degrees. Now you might also remember that when you graphed that on that window that I told you to use -90 to 90 for it, you got 5 periods of that graph, didn't you? And then you ran a line along here, and so you found all of these points of intersection, didn't you? Okay, so this one would correspond to the one that we found for 16.11 degrees. So you might say, well, why do I only get one answer when I solve this by hand? Well, the reason is because we're not taking everything into consideration that we have to take into consideration when we solve an equation in the general form. So the calculator is only going to give us the first answer it finds to the right of 0 that corresponds to this expression right here. Now we know that we had another solution over here, and if we traced it, I believe the next solution past this one was 52.11 degrees. And that was this one right here. And then you had another one out here in the positives that fit on that window too, and it was 88.11 degrees. But you also had 2 solutions back here in the negatives, and one of those was -19.89 degrees, and another was -55.89 degrees. Now, upon closer examination of this, we realized that there was a number right here in front of theta. And so that 5 theta meant that when I was multiplying by 5, that's like dividing by 1/5, isn't it? So if the value of a in our equation was 1/5, and the period for tangent is pi times the absolute value of a, then the period is 1/5 times pi. Remember, pi is 180 degrees, So 1/5 times 180 degrees means you have 36 degrees for the period. So we were actually looking at 5 periods of this graph, and we were trying to get all the points of intersection so we could get all the solutions in 5 periods of the graph. Now what you're going to notice about these solutions is that if you were to take 52 and 11/100 and subtract 16 and 11/100, you would get 36 degrees. If you take 88 and 11/100 and you subtract 52 and 11/100, you get 36 degrees. If you take 16.11 and you subtract negative 19.89, you get 36 degrees. And if you take negative 19.89 and subtract negative 55.89, you're going to get 36 degrees between these as well. So it just so happens that it works out that they're all 36 degrees apart because the period here is 36 in degrees. But I want to work with you on some techniques to help you know how to find all of the solutions and write them in what's called the general form. So to do that, I'm going to bring up this worksheet, 5-7, and you can read along on yours as we go here. It says you have already solved trigonometric equations over domains such as 0 to 2 pi. The goal of this lesson is going to be to consider and write solutions to equations over the entire set of real numbers. We know that the graph of the sine and the cosine and the tangent can go on in all directions toward negative and positive infinity. So we want to find what's called the general solution of any trigonometric function. To find this, you have to find all the solutions in one period of the function and then write the general pattern for all of the solutions. So we're going to find them in one period and then generalize them. To solve the trigonometric equation, we're going to use these steps. We're going to find the period of the function. We're going to write that down. Now, I've taught this for a number of years, and I know that everybody thinks the period of the function is always going to be 2 pi no matter what we have. And so it's very, very important that you find the value of a in the problem and then find one period of the function so that you're just looking at that one period to find all the solutions in one period. When you do that, then you'll be able to generalize it a lot easier. And we know from studying in the previous chapter that the sine of theta and cosine of theta, if we were to graph sine theta and cosine theta, the period of those graphs is 2 pi. If we have tangent theta, the period of that graph is going to be pi. All right? So 2 pi if we just have plain sine and plain cosine, and if we just have tangent, okay, it's when we get pi, but it's when we have something else in the argument of the function that gives us a different value of a that'll change that period that we need to watch out for. We're going to graph one period of the function using a window where we graph x min is 0 and x max is the period of the function. So we're always going to look at the first period to the right of 0, giving us some kind of positive values. The y min and the y max will be found by using the b and the k values. So we'll have to look at amplitude and vertical shift to be able to figure out if we're going to push the graph up or bump the graph down or extend it as far as amplitude is concerned. We're going to find any point or points of intersection or the zeros, depending on if we have the equation set equal to some number or to 0, and that are going to be graphed in one period of this function. We're going to write down the general solution, and if we can, we're going to find that general solution exactly. To do this, we're going to need to use our radian actor. So right now, before we get too far, we need everybody to pull out their radian actor. Hopefully you brought yours to class today. If not, you're going to have to be pretty smart and pretty savvy to know all of these decimals to know if they're exact or not. You can use your radian actor to check the solutions from your calculator, and if the solution cannot be found exactly, generally we will round to thousandths. So generally we would round to 3 decimal places unless you're instructed to do otherwise. The answers will be in the form of the first solution plus the period times n for all integers n, and then the second solution plus the period times n for all integers n, and so on and so on. There could be 3 solutions, 4 solutions, 5 solutions, however many solutions we have per period. We also could look for a pattern and describe the solution as that pattern if one exists. And I will show you some that I can help you with that will have a pattern. Okay, so here are the directions. It says we are going to describe the general solution in radians. If the solution is not exact, we're going to round to the nearest thousandth. Okay, I'm going to move this off to the side over here so that I can have my calculator open at the same time. So we're going to need to work on the calculator and work on the worksheet at the same time. We're going to kind of stay on the left-hand side and work several of the odd problems. We'll try to work all the odd problems if we have time, and then you'll need to go back and finish anything that's not done. So if there's some odd ones we don't get to, or even ones that we don't get done, then you'll need to go back and you'll need to complete all of those. Okay, our first equation says we have the cosine of theta is equal to 8/10. All right, the first thing we want to do is we want to write down the period of this function. This function is cosine theta. It's just like the parent graph of cosine theta. And the period of cosine theta is going to be, I think I need a drum roll here so you can get this. It's going to be 2 pi, isn't it? Okay. Then the next thing we're going to do is we're going to use what's called the intersection of graphs method. And by that I mean we are going to graph the left-hand side of our equation in our y1. So y1 is going to be the cosine of theta. Now, when we go to put that in our calculator, you'll notice over here on the graphing calculator, we only have one variable, and that's x. But on that button, there's also a theta, isn't there? So we might write cosine theta here, but when we go to type it in our calculator, we're going to use the x button. Our y2 is going to be 8/10. 8/10. Now what's going to happen is we're going to graph this, and the cosine graph is going to do something like this, isn't it? That'll be one period of that graph from 0 to 2 pi. And then there's going to be a line going across here at 8/10. And we want to find where the graph intersects that line. So we also know that we're going to be working in radians today. So the first thing I want everybody to do is go to the mode key on your calculator, and I want you to put your mode in radians. You've probably been hanging out in degrees for the last several assignments. We want to change that and work in radians. The next thing we need to do is we're going to go to our y equals. I'm going to clean out anything we have in here. Okay, and we're going to put cosine x, because x is going to stand in for theta. So cosine x goes in y1, and in y2 we're going to put 8/10. Okay, now we're going to go to our window. For our window, we know the period of the graph is 2 pi. So we want our x's on our window to go from 0 to 2 pi. We want to go everything from 0 over to the end of that first period, which is at 2 pi. Now when we want to decide upon a scale, it's kind of hard to know what to use for a scale. I don't like to get too many tick marks on there, but I don't like to have too few. And so I've kind of determined over the years that a really good scale is 1/6 pi. It's a good scale because 1/6 pi, if you had 2/6 of them, you'd have a 1/3 pi. 3/6 would be a 1/2 pi. So it works well for finding a 1/2 pi, a 1/3 pi, and a 6 pi. It's kind of a nice denominator. Plus it would give us 12 tick marks from 0 to 2 pi. So not too many and not too few. So I'm going to use 1/6 pi. 1/6 pi for the scale. Now you're also going to notice that when you put your x max of 2 pi in there, and also when I hit return here on the x scale for 1/6 pi, you're going to notice that it immediately turns those into decimals. So they're not quite exactly those amounts, but they're rounded for that. Okay, in front of the word cosine, we have a 1. And the 1 is the amplitude, which means this goes as high as 1, and it goes as low as -1. So if that's the case, -2 to 2 should be plenty of window range for my y max. So again, we're going to take into consideration when we do the y's, we're going to take into consideration the amplitude and any kind of vertical shift that we have. In this particular case, we have no k value, but we do have an amplitude of 1. Okay, I'm going to push graph. So here's going to come one period of my cosine function, and then I've got my line at 0.8. Very good. Okay, I'm going to hit my trace button, and I want to come over here and I want to trace where this point of intersection is between the line and the cosine curve. So I'm going to kind of get over in that neighborhood, go second trace, pick number 5 for intersect, enter, enter, enter. Okay, so my first solution that I find is theta is about 0.644. 0.644. Now I want to go to my radian actor, and I want to see if 0.644 is on my radian actor. And I see that it's kind of close to 2/9 pi, but it's not a number on my radian actor. So I'm convinced here that this is some sort of a approximation, 0.644. Okay, now I want to get the other point of intersection. So I'm going to hit my trace button. I'm going to go across here on my straight line, not my curve. Okay, and now I'm going to go second trace, number 5. And I come up with 5.640. 5.640. I'm going to look at that on my radian actor. Do I see that one on there? No, I don't. So I'm going to say my other solution is approximately 5.640. That would be to the nearest thousandth. Now, to finish these, I'm going to use my periodicity theorem that says I can find the next solution to the right or to the left by adding or subtracting multiples of this period, which is 2 pi. So I'm going to add on 2 pi times n to each one of these, and then I'm going to put a little bracket and say, for all integers in, for all integers in. So I could add on 1 times 2 pi, which would be adding on 2 pi, 2 times 2 pi, which would be 4 pi, 3 times 2 pi, which would be 6 pi, -1 times 2 pi, which would be -2 pi, and so on. Okay, now you don't have to do this, but I'm going to change my window here. I'm going to change it to go from -4 pi to +4 pi. Okay, now let me regraph this. And we'll get several periods of the graph going on here. Okay, so I'm going to go back to this 0.644 point. Okay, it's the first solution right here, just to the right-hand side of 0. It's on the way down. If I say 0.644 and I add 2 pi and trace that value, notice it's also right here at 0.8 on the way down. If I were to do 0.644 and subtract 2 pi, so that's 2 pi times 1, notice I have the next solution, it's just behind that. If I were to do 0.644 and subtract 4 pi, I would be at this solution on the way down over here. If I start at 5.640, which is the solution on the way up, it's the one on the where the function is increasing, then if I say 5.640 plus 2 pi, then I get the next one on the way up to the right of that one. If I went 5.640 minus 2 pi, I would get the one to the left on the way up. I could do 5.640 minus 4 pi, and I would get another one to the left. So you can see how we could extend this out forever and ever and ever, and just add on multiples of 2 pi. 2 pi times 1, which would be 2 pi, 2 pi times 2, which is 4 pi, 2 pi times 3, which is 6 pi, and so on and so on and so on. This then becomes our general solution. This is our general solution. Whoops, if I could spell. The general solution. In other words, it's going to help us find all the solutions to those problems, or to that particular problem. Okay, let's try number 3. On number 3, we see we have 2 sine squared theta is equal to 1 minus sine theta. Now, if we were to graph this side of our equation, 2 sine squared theta, 2 sine squared theta is going to be some kind of a curve. If I graph 1 minus sine theta, this side of the equation is also going to be a curve. It's kind of difficult sometimes to have a curve intersecting with another curve, particularly if they don't have the same period. You have a choice about, do I take the bigger of the 2 periods or the smaller of the 2 periods? How do I know when I've got all the points of intersection? It's really kind of difficult. So my advice to you on a problem like this would be to take the right-hand side of the equation, the 1 minus sine theta, and move it over to this side. And we'll set this equal to 0. Then the calculator can form one curve out of everything that's left, and then you can see where it's equal to 0. That would mean where it's going to cross the x-axis. Okay, so for the purposes of this problem, if I write down 2 sine squared theta, if I add sine theta over to this side, that'll make it a plus sine theta. And if I subtract 1 over to this side, that'll make it a minus 1. So when I move these two things on the right-hand side over to the left, they change signs, don't they? The 1 becomes a negative and the sine theta becomes a positive. Okay, now I can go over to my calculator and go to my y equals. And in my y equals, I'm going to put this side of my equation in the y1. So I'm going to type in 2 sine x, and then square it. I don't know if you remember this from the last time we worked with these, but there's no way to get the square right here by the word sine. So you want to go ahead and put your x, which is your representing theta, in parentheses as the argument of the function, and then square it. Don't put the squared inside the argument, put it outside the argument. Then I'm going to add my sine x and minus 1. Okay, so for my y2, I need to put a 0 in there. I need to put in a 0. Okay, which I did. And now I'm going to have to fix my window. By the way, what do you think the period of this might be? Well, we kind of have a dilemma. We don't know, because with a squared in there, we're not sure what's going to happen. But a good guess for the period would be just to look at it and say, well, there's no number or coefficient in front of theta, so that means a good guess probably would be 2 pi. But what you might want to do is write down 2 pi with a question mark, because if it doesn't work out, then we'll change that. Okay, but I think we should guess 2 pi on that. Oops, not 2 caret, but 2 pi. All right, so as far as amplitude goes, we do have a 2 in front of our sine squared, and we do have a negative 1 here, so we might need a slightly bigger window than negative 2 to 2. I'm going to go ahead and put negative 3 to 3 on here. If I need to adjust, I'll adjust it from there. I kept the x scale at 1/6 pi. Okay, I'm going to push graph. Okay, and this is what it looks like. And you know what? I'm looking at that and I'm thinking, gosh, I don't know. What if there's some other little bobbly thing that's going on over here? I don't know if that's the whole period or not. So a way to check that would be to go ahead and go to your window and double the 2 pi and make it into 4 pi. And let's just see what's happening over a bigger window. So here we go again. Okay, and now I clearly see that I have 2 periods of the graph, don't I? So 2 pi is the correct amount for the period. So I'm going to take my window and I'm going to change it back to 2 pi. But if you're ever in doubt, just expand that window out a little bit and look at it, and that'll help you see. Okay, we're wanting to know where it's equal to 0, which means where does it cross or touch the x-axis, right? And I see that that's happening over here 1, 2, and 3 spots. Okay, so I'm going to put my cursor kind of back here to the left, and I'm going to trace that point. And I come up with, on the trace, 0.524. 0.524. Now look on my radian actor, and this time 0.524 turns out to be 1/6 pi, doesn't it? Pi over 6. Okay, so I'm going to hit trace, and I'm going to go along here, come over here to the next point of intersection. And it is 2.618. So I look up 2.618, and lo and behold, it's on my radian actor, and it's exactly 5/6 pi, isn't it? Okay, so hit our trace button. I'm going to come over here and we're going to get the last one. And this last one looks like it's tangent. Looks like it's right on the x-axis, doesn't it? And it turns out to be 4.712. 4.712, which is 3/2 pi. So I have 3 separate exact amounts in radians for the solutions. Okay, and then for each of these I have to say plus 2 pi times n, so the period times n, and then for all integers n, so for every multiple of 2 pi. Now this is an example of one where if I go back to my graph and I look at it, and this was 1/6 pi, then I have 2, 3, 4, 5/6 pi, 6, 7, 8, 9/6 pi. And when I start looking at those and I look at 1/6 pi, 5/6 pi, and then 3/2, if I write 3/2 into 6, will be 9/6 pi. There is a pattern here, isn't there? It's adding on 4/6 pi or 2/3 pi each time, isn't it? So with that pattern, I could establish a pattern for this solution. And that pattern would be that you would have theta equals 1/6 pi plus, I'm adding on 2/3 of a pi, times n each time for all integers n. In other words, if I'm at 1/6 pi and I add on 4/6 pi, I'll be at 5/6 pi, and then that 2/3 pi would be 4/6 pi again, I'd be at 9/6 pi, and so on. So again, this would be a general solution. This would also be a general solution, but this is what we call the pattern. This one has a pattern to it. So your question is probably going to be, well, gee, do I have to find this pattern down here, or can I write the general solution and leave it like the one on the left? They are both correct. If it's easier for you right now to find this without finding a pattern, then by all means do that. If you see the pattern and you want to write the pattern down, then that's what you should do. They're both correct, and I will accept both of them. Okay, let's try number 5. For number 5, first thing we notice is that we have a coefficient in front of x. So if you were going to write this back in its stacked fraction form, How do you find the value of a by knowing this? Multiplying by pi over 2 is like dividing by 2 over pi, isn't it? So if 2 over pi is the amount of a, then the period of this function is going to be 2 over pi times cosine's period, which is 2 pi. Now when you get that, and these pi's cancel, that means the period of this function is 4. There's no pi in it anymore. It's just plain old 4. So every 4 units on your scale is going to repeat itself. Okay, you're also going to notice that you have some amplitude here and you have some vertical shift going on. So we're going to have to watch that when we make our graph. Okay. So for now, what we want to do is we want to go over to our y equals, and in here we're going to put 2 times the cosine of pi divided by 2, and then don't forget your x, which is standing in for theta there. And then on the other side of the equation, we can put -1. Okay, for my window, I'm going to take my window to go from 0 to just 4 this time. And maybe I'll go in increments of 1/4. That'll give me 8 increments. We could try the window from -3 to 3 with an amplitude of 2 right here, moving everything down 1. I'm not sure how that's going to work, but we could try that. Or maybe you want to try -4 to 4. Open the window up just a little bit more. Okay, we're going to go ahead and hit graph on that. And here's our picture. Looks like a perfect horseshoe type looking thing for the cosine and a line going straight across there. Okay, let's find this first point of intersection. Oops, you know what? I didn't put -1 in there, did I? That point of intersection, or that line of intersection needs to be -1. Sorry about that. It's a good thing I caught my mistake. It's going to make a big difference in my problem here. Okay. We'll back up to right here. And it looks like the first solution for theta is 1.3 repeating, which is 4/3, isn't it? It's 4/3. Okay, we'll buzz along here. Get over here to the right. And we trace that. 2.6 repeating would be 2 2/3, which is 8/3, isn't it? 8/3. And then we're going to say plus the period, which is 4 times n, and the period is 4 times n here also, for all integers n. So this one doesn't have any pi involved in it because the period was just 4. But once we get that period figured out, and we get the solutions figured out, we're going to add 4 multiples of 4 to it each time. So 4 times 1, 4 times 2, 4 times -1, and so on. Okay, it's time to go to page 2, number 7. The tangent graph. We haven't looked at any tangent ones yet, have we? Okay, when we do the tangent graph this time, we'll be able to put this in our y1, and we'll be able to put this in our y2. This is plain old tangent theta, and so remember the period of tangent, it's only pi. That's right. Okay, so we're going to go to y1 here, and we're going to put in the tangent of x. We'll go to y2, and we'll put in 1.5. And then we're going to go to our window, because it's all messed up. We're going to take this up to pi. And I still like my 1/6 pi increments, so I'm going to do 1/6 pi. Doesn't like that? No. 1/6 pi. Okay, and as far as amplitude, now you know when we graph a tangent function, normally we would have the boundaries be the asymptotes here at -pi/2 and pi/2, right? And the graph would look like this, and then it jumps over that line and it goes like this. Well, what we're going to see, change color here for a minute, we're going to see from 0 to pi over here. So we're going to see this branch of this graph and this branch of the other graph going like this. That's the only parts we're going to see. Okay? And so with that in mind, you might want a little more length on your graph. Maybe not -4 to 4. You may want to go, you could go -10 to 10, because the range on that thing is all real numbers. Okay, let me hit the graph. So here's that part of that first branch on the right, and here's the part, and here'd be that asymptote coming right in here. Okay, we've got one point of intersection. It's back this way, isn't it? Oops, don't want to go to 51. Let's go to 1. Okay, I'm going to get intersect. And I see that it's intersecting at 0.983. 0.983. 0.983 isn't anything on my radian actor. I hope it's nothing on yours unless you have some wrong number there. So we're going to say theta is approximately 0.983 plus the period times n. So we're going to say pi times n for all integers n. For all integers n. Okay. I'm going to leave you to do number 9 right now. Number 9 should be pretty simple for you. So I'm going to go ahead and just pause the recording for a minute. Let you work on number 9, and then I'll join you back up. Okay, I hope you had good luck doing that problem. The period should have been 2 pi. And for the solutions for number 9, even though 0.1234 is a pretty cool number, it doesn't come out that nifty when you trace it, does it? Approximately 1.447 plus 2 pi times n, and approximately 4.836 plus 2 pi times n for all integers n. Okay. If you got that, good job. Let's try number 11. We have 5 sine x is equal to 8. Let's think about what's going to happen with this for a minute. We're going to have the sine function with an amplitude of 5. So it's going to do something like this, isn't it? Where, let's see, it probably starts if it's maximum there. No, it's going to start down here, isn't it? Go like this. Okay, so it's going to max itself out at 5 here. Its minimum is going to be at -5. Okay, and then there's going to be a line going across here at 8, isn't there? What's the period of sine x? 2 pi. Oops. So if I do 5 times the sine of x, and I do an 8 right here, I'm going to set my window to go from 0 to 2 pi. Okay, now I can't really go -5 to 5 because the amplitude on this is 5, but I have to include the number 8. So if I wanted to go -6 on the bottom, I'm going to have to go at least 9 or 10 on the y max. Let's try that. Here's my sine function. There's my line at 8. Where do they intersect? Well, they don't. So if they don't intersect, and I'm using the intersection of graphs method, then that must mean that there are how many solutions, or how many points of intersection? And that would be none. So this is an example of no solution. No solution. So you can get trig problems that have no solution, just like you can on any other kind of equations that you solve. Graphically, it looks like this picture right here, or what's on your graphing calculator. Now, if you were to solve that problem by hand, what you would have done is divide both sides by 5. 8 divided by 5 is 1.6, isn't it? And then to solve that, you would have had to done the angle whose sine is 1.6. And when you try to take the inverse sine of 1.6, your calculator gives you a domain error, doesn't it? Because this is larger than 1. We can't have any numbers outside of the domain of -1 to 1 on the inverse sine. So that wouldn't have worked. Okay. I don't know what you think about problem number 13, but most of the time if I see a problem that has a square root in it, I think to myself, well, that's not going to come out very nice. This one is 2 sine theta minus the square root of 3. So once again, what's the period of sine theta? It's just like the parent graph, so the period is 2 pi. Let's try putting that in our calculator. Okay, so I have 2 times sine of x is, or minus the square root of 3 is equal to 0. I go to my window, the period is 0 to 2 pi. This one has some amplitude and some phase shift going on here, but when I think about it for a minute, I'm thinking I'm going to try -4 to 4. How's that sound? Well, sounds pretty good, except I don't really need all that room at the top that I left, do I? Okay, so it crosses the x-axis here because I have 0 in 2 spots. And let's see if we can find out where those 2 spots are. The first one is at 1.047. 1.047, if I check my radian actor, is at pi over 3, exactly at pi over 3. I'm going to buzz over here to this other point of intersection. And it is at 2.094. 2.094. 2.094 is 2/3 pi. Now, sometimes when I see I have 1/3 pi and 2/3 pi, I think there might be a pattern to this. But you can see that the next ones are way down here, so I don't think there is there's not an increment, equal increments all the way across. So then I'm going to put plus 2 pi n for all integers in. And there we go, there's our general solution. On number 15, the most difficult thing about this one, I think, is going to be figuring out what's going on when you have squares and then when you have this number in front and a number over here and so on. Will the period really be what we think it is, or will it be a little bit bigger, a little bit shorter? We notice, first of all, that we have a number that's the coefficient of x. So we think, all right, if we're multiplying by 3 is like dividing by 1/3. So the a value should be 1/3. And so if we take 2 pi times the absolute value of 1/3, we're going to get a period of 2/3 pi. So we think the period might be 2/3 pi. Well, we're going to try that. We're going to type in 2 cosine x, and then remember after you 3x. After you end the parenthesis, Then you do the squaring. You can also use the caret and the 2 if you'd like. And then minus cosine 3x. And we're going to set that equal to 1. So I'm going to go back and double check that. Looks pretty good. My window needs to be set from 0 to 2/3 pi. 2/3 pi. Okay. And then when I'm thinking about this in terms of what it's going to happen with the 2 cosine squared part and then the minus in front of here, I mean, I could leave it on -4 to 4. I don't know if we need that much room or not. I'll try that. We'll see what it looks like. Okay. Would you say that's 1 period of that graph? I would say it is. All right, so let's see if we can find those points of intersection. Okay, the first one is way back over here at the beginning. Okay, so I think it's right back in here. So I'm going to go second, trace, go to number 5. And when I do that, my calculator does some thinking, and then notice where it takes my cursor? It's way over here at 2.094. And I'm saying, wait a minute, I thought that the point of intersection was way, way, way over here. And so what do you think that point of intersection is over there? Well, turns out that it's at 0. If I hit trace and I tell it to go to 0, at 0 am I at 1? And at 0 I'm at 1, so it's actually 0. But sometimes the rounding error on the calculator will take you clear out here to the end of the period. Okay, so I'm going to write that solution down. We got 0. The next one is at 0.698. 0.698. 0.698 just so happens to be 2/9 pi, doesn't it? Okay, this third one here is 1 point, let's go 396. 1.396, that's at 4/9 pi, isn't it? Okay, and then we know we have one more out here because the calculator took us to that one earlier when we were trying to get that 0 over there. And it was at 2.094. 2.094 is 2/3 pi. Okay, which happens to be exactly 2/3 of a pi away from 0. So these are essentially the same. This one and this one are essentially the same because they differ by the amount of one period. Okay, so we could write that theta is equal to just 2/3 pi times n. You can write 0 plus 2/3 pi times n. That'll take care of both of these. And then you can have theta is equal to 2/9 pi plus 2/3 pi times n. And then you can have theta is equal to 4/9 pi plus 2/3 pi times n. And then you could say for all integers n. If you go back and look at this though, this is 0/9 pi, 2/9 pi, 4/9 pi. 2/3, if I write 2/3 in terms of ninths, would be 6/9 pi. So they're all how many ninths apart? And that would be 2/9 apart. So the pattern for this one could be written as all the multiples of 2/9 pi. 0, 1 times 2/9, 2 times 2/9, 3 times 2/9, and so. So this would be for all integers n. If you wanted to find the pattern, this would be the pattern. This is a fine general solution over here. You can use that no problem. Okay, I think I'm going to skip number 17 for the time being. Let me see if there are any more interesting ones I think I want to talk about with you. Don't be fooled by numbers in front of here on 19. On 19 is still just sine theta, and the period of sine theta is going to be just plain old 2 pi, isn't it? Okay, let's talk about 21 for a minute. 21 has some interesting things going on with it. First of all, you see that it says we have the cosine of 2 theta for the first term, and then the other term is just plain old cosine theta. And so when you're looking at a problem like this, I mean, they don't put parentheses around here, but I will just to show you for the sake of showing you, that you could argue that you don't know what the value of a should be. For this term, multiplying by 2 is like dividing 1/2 by 1/2, so you could argue that, you could argue that a is a half, but then here you could argue, well, a is really still 1. If it's a half times 2 pi, then the period is only pi. If it's this one, then it's going to be a period of 2 pi. And so the question is, well, what should I use for the period of it? Well, the answer to that question is you should use the bigger of the two amounts. And then if you graph it and you see that the bigger of the two amounts is too much, then you can always back it off. But if you graph it on the smaller of the two amounts and then you're not sure whether you have a period or not, you're going to have to check it by doubling it anyway. Okay, so we're going to go over here to the calculator and we're going to type in the cosine of 2x plus the cosine of x, and then a plus 1. And then we're going to have a 0 for the other component on this side of the equation over here. Okay, so we think the period of this is 2 pi. And I don't know if we need all this height or not. I'll take -3 to 3. Let's see if that works. Okay, so let's check it out. Okay, do we have one full period of the graph? I believe we do. I believe we do. Okay, so what we're going to do is we're going to come down here and we are going to trace this first point of intersection. Looks like we have more than one. And in fact, if I wanted to get rid of some of this bottom window part, I could. And you might be able to see it crossing a little bit better. You'll still get a full view of it. Okay. Now I'm going to show you another little trick here. If you don't want to always look everything up on your radianactor, your calculator just calculated a trace point. In other words, we told it to go to second calculate, or second trace, which is calculate, and we told it to come down and do number 5, which is find a point of intersection. And it came up with 1.571, which we could look up on our radianactor. But if you wanted to, you could hit clear twice, and then if you just hit enter, you just take that answer that you got there and say divided by pi, and divide the pi out of there. No, that's not going to work. I messed it up. Hang on. Let me go back to my graph. Okay. I'm going to calculate this. Okay. All right. I'm going to hit clear twice. And then I'm going to tell it to take that answer and divide it by pi. So I'm going to divide the pi out of there, and I get 0.5. So that tells me that that answer is really 1/2 pi. 1/2 pi. If I were to look up let's see, what was that again? 1.537, I believe it was. No, 1.571. I'm not quite on my trace point anymore, am I? 1.571, it would be 1/2 pi. If I come forward to the next point of intersection, it's 2.094. If I hit clear twice, and I tell it to take that answer, divide it by pi, divide the pi out of there, I get 0.66666. If I don't know what that is, I can hit math to enter. Whoops, that didn't work. Anyway, if I did it right, it would tell me that it's 2/3 pi. It's hard with my pen sometimes. Okay, let's go back to my graph. Let's find the next point of intersection. It's at 4.189. 4.189. I could look that up on my radian actor, but I could hit clear twice. Say take the answer that I just did and divide the pi out of there. And then go to math, enter, and it gives me 4/3 pi. Then last but not least, if I go back to my graph, trace this one, 4.712. If I hit clear twice, take that answer and divide by pi to get the pi out of there, I get 1.5, which of course is the same thing as 3/2 pi. Okay, so now I have all 4 of my answers, and each one of them gets plus how much? 2 pi n. And that would be for all integers n. For all integers n. Okay. I really think that you'll be able to do these problems. I don't think you'll have too much trouble with them. I'm going to leave you in the fair and capable hands of Mrs. Kinner-Kennett as your substitute. The back page of this worksheet is a practice quiz. You'll need to do that to practice for your quiz for next time. If there are any problems or concerns on this quiz, be sure and come to see me about this. This quiz will be on Friday. I want to caution you that when you get back onto this page, you need to take your mode and put it back into degrees. Your quiz will be over law of sines, that triangle formula that we learned, that using side angle side, and converting things into exact radians, which we do by doing them in degrees. So when we do these equations, a lot of times we're going to have our calculator put in the radian mode, but I want to put you back in the degree mode.